So what is the Robinson annulation? Well, if we're breaking it down, Robinson's just the guy who came up with the annulation. And annulate means to have rings or be a part of a ring. So if we know that our ending product is some sort of an annulation, so some cyclic molecule, then we're going to start with anything that's going to get us to that part. And the way that Robinson came up with it was to do it with some sort of a ketone or an aldehyde, and also um, an alpha beta unsaturated carbonyl. So what does that look like? Simplest form I can come up with and show a good mechanism is one with acetone as our starting material. So using acetone, next thing we're going to do is we're going to combine it with some base. And so the base that we're going to use for this is just going to be hydroxide, and we have this proton sticking out right there. And so we're going to go ahead and pull that off. And when we do that, we have to move electrons all the way around. We get to this part, and this is now where you'd administer the second step of the Robinson annulation. So that'd be adding our second reactant, which in this case, it's going to be our alpha beta unsaturated carbonyl. So what happens? Following the highest energy thing, electrons will come down to remake that carbonyl. When they do that, these electrons have to break. They'll break through that carbon, and they will attach to this alpha beta unsaturated aldehyde via a Michael addition. Or if you're not comfortable with the Michael addition, you can also call it a 1,4 addition / Michael addition. Great. So when we do that, we're not finished with the mechanism here yet. When we do that, we of course have to move electrons around, and we get something going on like that. So what does our product now look like? Well, it looks like we are, for the most part, reforming that acetone, and from that carbon, it is attaching to 3 other carbons, and so I'm going to draw 3 carbons. So there's 1, 2, and there's the third. So let's see, 1, 2, 3. Now on that third, we have that O minus that was formed via the Michael addition. And we also have that double bond, which is now right here. So going back a little bit, when that OH minus, so when our hydroxide pulled off that alpha proton, we created water, which we're going to use as a base, as an acid here. It'll pull off, our enolate will pull off that proton, pulling it off. And from there, we get to this intermediate. So we have our enol formed, which is great. And now, what do we have in solution? We have hydroxide. And so any guesses to what we're going to do? Just going to tautomerize. So I'm going to write on the bottom here, tautomerize. And I'll go ahead and go through it. Just real quick, let me make this H more obvious. So quick tautomerization, the proton gets pulled off. When that happens, I'm going to skip a step in the mechanism, reform that double bond, and when you do that, you now have the electrons being pushed onto that alpha carbon, which will get you to right here. electrons right there. And then now, see, how can I do this? Like that. Now again, from hydroxide we added a proton, so now we have water, and we have something basic, and so water will act again as an acid. And so we're going to treat it just like that. We are now at our next intermediate. Oops. Looks just like that. So now we have a decision. We now have hydroxide in solution, so let me draw the hydroxide, and we have to figure out something to do with it. So options are options. We see that there is an acidic proton right here. We have another acidic proton right here, and then one more right there. So which proton is this hydroxide going to want to pull off, or is going to be more likely to pull off? And the answer is, well, it's going to be this one on the far left side. And the reason for that being that if you pulled off this proton, and I'm going to call it, I guess, like this orange color, proton 1, if you pulled off that proton, then you would get your annulation, you'd get a cyclization, but it'd be a 4-ring cyclization. So 4 rings, this is, 1, 2, 3, and cyclize all the way to that carbonyl. So that's only 4. And then again, if you did it with, we said this was the second proton you could possibly pull off, then again, you'd have a 4-carbon ring. So that's 1, 2, 3, and 4. Fourth being that carbonyl on the right. And then testing out, what about our third proton that we could possibly pull off? Well, if we pulled off that proton, we'd then have a 1, 2, 3, 4, 5, 6 carbon, a 6-carbon ring, which is a lot more stable than having a 5-carbon ring, of course. And so that will be the proton that gets pulled off. And so let's go ahead and do that. So let me draw this proton in. Let me draw it right there, I guess. And our hydroxide comes over, pulls it off. When it does that, I'm going to draw the electrons going onto the carbon. We will now get our next intermediate, which is this molecule. And can you see what's going to happen next? Well, if you have a model kit, you can make this, and you can see that our single bonds are going to be able to rotate completely around each other, so that we can get these electrons interacting with the carbon of that carbonyl. And so it will happen. You'll have a nucleophilic attack, and the electrons from the carbonyl will bounce up to the oxygen, giving you our next intermediate. And we have a 1, 2, 3, 4, 5, 6 carbon ring, we said. And so I'm going to draw a 6-carbon ring. That looks pretty good. 1, 2, 3, 4, 5, and 6. Not bad. We have a carbonyl in the middle, and then 2 away from that will be our other carbonyl. So 2 away would be our carbonyl. So this was, let me show you what I'm talking about. So from this carbon, it attached to our carbonyl. So from this carbon, it attached to our carbonyl right there. So that is where our carbonyl should be. And just like that, but of course we got ahead of ourselves. This should be a minus. Now at this point, we have water floating around in solution, so we're going to let water act as our acid again, so that this O minus can pull off that proton, just like that. We now ended up with this now down here, and I'm running out of room slowly. Oops, there we go. Getting a little bit better. Oh, we said OH. Now, what do we have floating around in solution? Well, it's more hydroxide. So there's our hydroxide. Do we have any proton we can pull off that wouldn't just put us back in reverse? And the answer is yes, we do. We have a proton right here just hanging out. So hydroxide will pull off that proton. When it does that, it'll flop down to make an alpha beta unsaturated ketone, and at the same time when it does that, it can kick out hydroxide. This is the one of the very few times where you can actually allow hydroxide to be a leaving group, and the reasoning being that you're in a basic environment. So if this was an acidic environment or a neutral environment, you could not kick out hydroxide because it wouldn't. Kicking out hydroxide would create a basic solution, and if you're already in an acidic solution, you couldn't create something that's basic. So we've now gotten to this part, and essentially finished our synthesis. And for the heck of it, I'll just say what we kicked out. We just kicked out some water. And at this point, it is non-reversible. So this would be how we would make our alpha beta unsaturated ketone in a 6-member ring via the Robinson annulation.